If one was to look into the discovery of carbon nanotubes, the first name that would surface would be Sumio Ojima. Ojima discovered these extremely small tubes of graphitic carbon in June of the year 1991. Ojima found a very thin, needle-like material when looking at the core of carbon material under an electron microscope. This new and exotic substance was proved to have a graphitic structure. Ojima called these materials carbon nanotubes due to their tubular structure of carbon atom sheets, with a thickness measured by less than a few nanometers. Shortly after his discovery, Ojima published a paper about the carbon nanotubes, which sparked a frenzy in the scientific and physics community. In today's world, one can find carbon nanotubes in everyday objects such as baseball bats, golf balls, and car parts.
A carbon nanotube is a tube sheet material made up of carbon. It measures on the nanometer scale, hence the name nanotube. There are many types of nanotubes, but it is categorized into two groups, single and multi-walled. The wall part comes from how many layers it has. The wall is held apart by interatomic forces. The four methods to making nanotubes are arc discharge method, the laser method, the chemical vapor deposition, and the ball milling method. In the arc discharge method, voltage is discharged from the rod. After heating and vaporizing the carbon, it forms into CNTs. In the laser ablation model, a laser heats the carbon, then vaporizes it, turning it into CNTs. In the third method, the chemical vapor deposition, the substrate is exposed to a volatile pressure, which then reacts and decomposes to form the nanotube. The third method is also the most common way of creating CNTs. The fourth method involves placing graphite powder into a stainless steel container. When the container gets purged and argon gets added, the machine keeps grinding till the powder turns into CNT. Some new ways of creating CNTs use flame synthesis, electrolysis, solar energy, and heat therapy of the polymer.
The economic possibilities for the use of carbon nanotubes are endless. Similarity to human skin makes it an optimal choice for developing carbon nanotube-based synthetic skin. Furthermore, it also has a self-healing property, which is another reason carbon nanotubes are the optimal choice for synthetic skin. Furthermore, it is also used in large volume applications in battery electrode additives, plastic additives, fuel line systems, etc. However, because of the high energy cost of creating these nanotubes, it is not expected to be used for large-scale projects for another few years. Such large-scale projects include, but are not limited to, photovoltaic devices, flexible electronics, and power transmission cable.
The size, surface area, and adsorption properties of the carbon nanotubes make them the perfect membrane for filtering out substances from water so that it is safe to use and drink. This allows it to filter out toxic chemicals, dissolved salts, and biological contaminants. Carbon nanotubes in tennis rackets are effective because they increase the control and power in the frame of the racket. They contribute to the lightness and strength of the racket because of the cylindrical shape and size, and they also contribute to the dexterity of the racket.